Hi, my name is Jeongseok. I'm going to talk about ObliCheck, which is a joint work with Griffin, Rishabh, Raluca, and Koushik. Encryption protects data sent over network and stored in disk. Even more, hardware enclaves like Intel SGX encrypt data processed in memory. However, does encryption completely hide your confidential data? Even if your data is encrypted, access patterns to the data can still leak sensitive information. Common data access patterns include access to memory addresses and network addresses and size of messages sent over network. Here's an example of data access pattern leakage. Let's say there is a hospital and an attacker wants to learn about sensitive patient's data. A patient Alice has flu, so a doctor sends an encrypted query to the server to see patient's records with flu. Another patient Bob has cancer. In this case, however, because cancer is much more rare than flu, the size of the returned result is much more smaller. By combining this information with the known frequency of diseases, the attacker can potentially deduct Bob has cancer. So how can you prevent access pattern leakage? One naive approach would be just to make dummy access to every record in the database. Then, the memory access pattern always look the same. Then the attacker cannot distinguish those two queries. This type of property is called obliviousness, which means that the access patterns are independent of the sensitive data content. Numerous oblivious algorithms have been devised so far. Oblivious algorithms, such as sorting network, are much slower than regular sorting algorithms. To improve the performance, recent oblivious algorithms typically assume a certain storage such as register or hardware enclave is not observable and leverage it to improve the performance. An attacker cannot see the content and access patterns of the data inside unobservable space. In this sorting example from Opaque, it uses unobservable space to sort the records using fast regular sorting algorithms such as quicksort. This reduces the use of sorting network and improves the overall performance. Oblivious algorithms conceal access pattern leakage, but it is complicated to be both oblivious and efficient at the same time, which makes it difficult to check when one is indeed oblivious. Still, algorithm designers and the users have to write and understand the proofs of the algorithms manually. So how can you automatically check oblivious algorithms in a practical way? Unfortunately, existing solutions are insufficient when an algorithm uses unobservable space. I put an example code which is an excerpt from the oblivious filter algorithm. The program processes input private data, compares each element to value, and tags either 0 or 1 based on that. Here we simply assume an attacker can only observe network access patterns. This program adds a single element to the output buffer every iteration regardless of the value of E. So the length of the output buffer stays always the same. Also, the output buffer is encrypted before sent over network, so only the length is observable to an attacker. So the algorithm is oblivious. The first existing approach is taint analysis. In this approach, a checker does taint analysis to check if there is any branch condition based on private value. If so, it rejects a given algorithm. From the private data variable, the checker propagates the taint throughout the execution. The variable E in the for loop is tainted. This branch condition thus contains a private variable E. Since the checker found a problematic branch predicate, it rejects this program. However, this program is actually oblivious, so this is a wrong judgment. Another existing solution is to use symbolic execution and check every program execution path meets the obliviousness condition. Symbolic execution runs the program with symbolic input and diverges the execution at every branch with symbolic variable. However, symbolic execution is insufficient as well. When the symbolic execution engine encounters the branch in the first iteration, it forks the execution into true and false path. In the second iteration of the loop, now the total number of paths becomes 4 because each execution path is again diverged into 2 paths. As you saw, the time of symbolic execution grows exponentially as the input length grows. This problem is called path explosion, which is a widely known limitation of symbolic execution. To overcome the limitations of existing approach, we devised ObliCheck, specialized for verifying oblivious algorithms. Here are the core ideas. First, we let the user specify what is observable and unobservable access. ObliCheck provides API for programmers to do so. We leverage domain-specific knowledge of Oblivious algorithms to improve the performance. Optimistic state merging is a technique for ObliCheck to merge different unobservable states. Finally, we improve the accuracy of ObliCheck by removing the false positive with iterative state unmerging. I'll first explain the ObliCheck API. When an algorithm designer uses ObliCheck, he or she uses predefined APIs to access observable space. When an API is called, a trace is added to the access sequence under the hood. In the example program, because the network is assumed to be observable, this send function is replaced with the ObliCheck send API. It keeps the trace including the address and the length of the output and uses the trace to check the obliviousness. Now I'll explain how ObliCheck leverages the domain-specific knowledge for optimistic state merging. Since ObliCheck can now know which part of a program state is not observable, it can merge those states with some over-approximation. Let's see how optimistic state merging works. When ObliCheck encounters the branch, it forks the execution. In both of the two paths, a single element is added to the output buffer, the pair 1, E0, which is the first element of the private records, and the pair 0, E1 respectively. After executing the append function, the relevant program state looks like this. In traditional state merging, these two states cannot get merged because the output 0 has different values. To be more accurate, the combined path should carry these two different states with complicated path conditions. Here we utilize the domain-specific knowledge. In Oblivious algorithms, we assume that the actual values are in the unobservable space, so an attacker cannot distinguish 1 and 0 since the attacker only watches the encrypted data. Based on this domain-specific knowledge, ObliCheck over-approximate these values and replace them with symbolic variable which can be an arbitrary value. We put star to denote this in the code. So after calling the append function, output 0 now stores the star instead of 0 and 1 in both paths. To implement this, we make ObliCheck introduce a new unconstrained symbolic variable which can be an arbitrary value. We call it S0 in this example. Now the output 0 has the same value in both paths, so we can merge the two states completely. Now in the second iteration, we only have one merged path or state. It again diverges when the engine encounters this branch. But ObliCheck applies the same optimistic state merging process and merges the states. Now the number of states stays linear. After finishing the for loop, the program state looks like this, and this is the only reachable state of this program. And therefore, ObliCheck reports the algorithm is oblivious since the output buffer length is always n in all paths. Optimistic state merging improves the performance, and this is based on over-approximation, so the transformation is sound. However, our optimistic state merging can bring up some false positives because it is over-approximation. To solve this issue, we devised iterative state unmerging technique. Here's an example code starts with the same filter code. I extended the code with a for loop that transforms an element based on the tag. This algorithm is oblivious because output 0's first element is 0 or 1, so t.first is either 0 or 1, which means that result the length always increments by 1 and stays the same regardless of the output records. If we apply our state merging to this program, the first field of output elements can merge to S0. Because S0 is not constrained, the symbolic execution considers the case where S0 is neither 0 nor 1. The result length is 0 in this case, which is different from the result of other branches. Therefore, this program is reported as non-oblivious, which is a wrong judgment. How should we handle this issue? In symbolic execution, it is difficult to know how the value will affect other values later in the program. So ObliCheck does in an opposite way. It merges every value first and checks if the program is oblivious. If not, it iteratively unmerges symbolic values included in the verification condition. Here's the original program. ObliCheck first runs the program symbolically using our merging technique. However, when ObliCheck runs the program, it maps the symbolic variable to their location where the variable is introduced. Later, program is reported as not oblivious, so it runs the program again. In the second iteration, ObliCheck does not merge state at the saved operations. Now, t.first is concrete value which can only be either 0 or 1 because the opposite 0 can be only 0 or 1. So there is no case where the t.first is neither 0 nor 1, so the result.length stays always the same. As a result, ObliCheck reports the algorithm is oblivious after this round of execution. This technique makes ObliCheck achieves better accuracy, but the extra program execution increases the analysis time. However, we found that the extra cost is tolerable in reality because our target programs are nearly oblivious already, and the first iterations are quite fast because most states are merged. I'll briefly show our evaluation result. These are the tested oblivious algorithms. The first two are basically the two examples I already demonstrated in the previous slides. This column shows the correct classification of the oblivious algorithm. As you can see, taint analysis rejects all programs because they all contain secret dependent branches and only get one case right. In contrast, ObliCheck accurately classifies oblivious algorithms as shown here. The second evaluation is regarding the performance improvement. ObliCheck achieves from 200 to 15,000 times performance improvement compared with symbolic execution. To conclude, we devised optimistic state merging and iterative state unmerging techniques based on the distinction between observable and non-observable state. We showed ObliCheck can check the algorithms far more faster than symbolic execution. Thanks for watching.